we're going to be doing proofs of angle properties and proofs of segment properties as well. So first off, when we say a proof, so far we've done algebraic proofs, which kind of follow a formula where we're solving an equation and we use the properties of equality to kind of justify each step. Geometric proofs are going to be slightly different. When we're doing a geometric proof, we'll have some sort of conjecture or conditional statement that we're kind of trying to prove, where we start off with a hypothesis and we use any definitions or postulates, properties, theorems, any of these things that we know to show that the conclusion must be true. Using those, we need to create that sort of a chain of reasoning or a chain of steps that go from that initial statement, what we know to be true, down to the conclusion. That process of actually creating that chain can be tricky, but that's what geometric proof is. So let's look at an example here of a proof. This one's somewhat complicated, but better to not start off with something too easy. So here we have a conditional statement. If angle A and angle B are complementary and angle A is congruent to angle C, that's what that's supposed to be, then angle B and angle C are complementary. So the beginning of our statement, the hypothesis, this is what we can start off with. This is what we call our given information. It's what we can assume to be true from the very beginning. So we can assume we have these two angles, which are complementary, and angle A is congruent to angle C. And the second part, the conclusion, angle B and angle C are complementary. This is what we need to end with. This is what we are trying to prove. So notice that what we are trying to prove is always going to be this last statement. So whatever our proof ends with, that's what we were trying to prove, which in this case is two angles are complementary. All right, so all the steps are kind of shown out here, and I'm not expecting us to be able to kind of write a proof like this quite yet, but eventually, with some more practice and seeing some more examples, we could probably get here. So the first step, and this is generally something that we're going to do a lot, is in the beginning steps of the proof. So in this case, in step 1 and 3, I would have probably, if I was writing this proof, I would have probably done this as my second step. But that's just a minor difference. I just like to generally, anything that's given to us in the beginning in the hypothesis, I just like to kind of list that at the beginning. These proofs are not going to be just one step and another step and another step and another step that all follow through like the algebraic proofs are. These ones are going to be a little less kind of straight down. We might take 2 steps to say something and then another 2 steps to say something else, and those will kind of come together to make another statement later on. They're not going to be quite as linear, following a set path. That's what can actually make them somewhat complicated. All right, so we're starting off with angle A and angle B are complementary. That's one of our 2 pieces of given information here. And then directly from that lets us set up this equation right here. Step 2 is directly based on step 1. Because we know they're complementary angles, we're allowed to set up this equation, because that's what it means to be complementary. It means they add together and equal 90 degrees. Then step 3, that is another piece of our given information right here. Angle A and angle C are complementary. And then directly from that, since we know since they are congruent, so angle A and angle C are congruent, that means that their measurements are equal. That's what it means to be congruent angles. It means that the measurements are equal. Then, and this step right here, this is kind of the key to this particular proof. And a lot of proofs are going to have this. They're going to involve starting with an equation, some sort of an equation that we can set up, and then substituting in that equation. And that's what happened here. We took the measurement of angle A and we replaced it with the measurement of angle C using the substitution property of equality. And we're allowed to do that because of step 4 right here. Since A and C, since those two angles are equal to each other, anywhere we have angle A, we're allowed to replace it with angle C. So that's what we did. We used the substitution property of equality to replace that. And then that gives us this nice equation right here, that angle C plus angle B is equal to 90. This is kind of mathematically what it means to be complementary angles. It means those two angles add to 90 degrees. Therefore, based on the definition of complementary angles, since they add to 90, we can say that they have to be complementary to each other, and we concluded our proof. Again, this is not as straightforward, one step follows the next, as those algebraic proofs we're doing, and that can be really tricky. In fact, the way that we create these proofs are not going to be one step and then the next and the next and the next until we reach the end. We're going to kind of start at the beginning, know where we end up, and kind of work from both sides until we've connected a nice chain of logical steps down to the conclusion. And again, we'll go through several examples here, so make sure that if you're having questions, make sure to ask. All right. So here, the next few slides, I just have some definitions that we're going to be using. These are going to be justifications or reasons. These are things that we're going to be able to put in the right side of our proof. So the definition of congruent angles, the definition of a right angle, the definition of supplementary angles. I wrote these all as biconditional statements because that's the way we want to do our definitions in geometry. I'm not going to read each one of these out. We kind of have seen these before, maybe not as a biconditional statement, but we know what they are. We'll just kind of use them as we're going. So here's 4 of them, and I have 4 more on the next page. So next page, some other definitions we'll need to know: an angle bisector, congruent segments, midpoint, straight angle. All these things are things we're going to need to be able to use as reasons during our proofs. One of them that may seem silly is this one, congruent segments, and also similarly congruent angles. It's just really important to know when you say two things are congruent, technically that's not the same thing as saying that they're equal. It's true that they're equal. So if we know that we have two congruent segments, then that's going to tell us that the lengths of those segments are equal to each other. So we'll be doing a lot of times where there will be kind of two separate steps that seem like they're saying the same thing, where we have two segments are congruent, and then we just say the segments are equal. Eventually, we might be more relaxed with that, and we might just kind of interchangeably use these ideas, but it's important to know they do mean something just slightly different. And then the other thing here, a straight angle. We may not have formally defined this, but there is an object called a straight angle. It's basically a straight line. And a straight angle, we say that its measurement here is always 180 degrees. The reason we have this is because we do need to use it to make some proofs, especially about linear pairs or some other things like that. So we'll use this definition actually in a proof that we're going to do here in a minute. Okay. The next thing is just some other things that we'll use as reasons that are not definitions. We have all the properties of equality. So these 4 right here, these 4 right here, the addition, subtraction, multiplication, division, those are all the ones that are going to be involved when we're solving an equation, or we add to both, we've used these already. These are going to be ones that are used a lot more in geometric proofs, the substitution property and the transitive property, than they were used in the algebraic proofs. So we're going to use these 2 properties in particular a little bit more than we compared to when we were doing algebraic proofs. Then we have anytime we set up an equation involving segments or set up an equation involving angles, we often are going to be using these 2 postulates. Remember, the segment addition postulate basically says if you have a segment and you cut it into into two smaller segments, then the whole thing needs to equal the two pieces added together. All right, that's our segment addition postulate. Big segment divided into two smaller segments makes sense. The whole thing equals the two pieces added together. Same thing with angles, right? When we're talking about angles, if you have an angle that's been divided into two smaller angles, well, the whole angle will equal the two pieces added together. So whatever this meant, keep doing that. Whatever this measurement is here plus this one needs to equal the whole big angle. Same idea, and we use it for setting up equations, so we'll need to do that a fair amount when we're doing angle proofs. Okay, so I'm going to try to do 2 example proofs. Again, these aren't things that you'll necessarily be able to do at this point. The first one that we're going to do is we're going to do a proof of the linear pair theorem. So I'm going to go ahead and state it right here and just kind of make sure we understand what's going on with it, and then we'll prove it. So the linear pair theorem says that if 2 angles form a linear pair, that's what this is, together they make a straight line, then they are supplementary, meaning they have to add together to be equal 180. Right? Key here with this proof is when we're talking about a proof like this, we have to remember that a straight angle, a straight line, has a measurement of 180. That's going to be involved in this proof. So I'm going to be using 2 concepts, and I'm just going to kind of set out a plan for what we're going to be doing here. I'm going to say that I know that angle COA, that's the one that I drew right there, the straight line, I know that equals 180. And I also know that angle COA equals angle 1 plus angle 2, right? If I add those together, that's using my angle addition postulate. And then another thing I can do is, since I know COA equals 180, I can actually just make a little substitution. I can put 180 right in here for angle COA. So this is like a really rough plan of what my proof is going to look like. And then that gets me basically right here, that angle 1 plus angle 2 equals 180. I'm not using proper notation necessarily in here. Technically, these should all have a little m for the measurement in there, but we get the point. That's going to be the basic outline of what this proof looks like. All right. So here's a space for us to do this. Generally, when you're proving something, the very first thing is you start off with your given information, in this case, the hypothesis. So angle 1 and angle 2 form a linear pair. I'm just going to abbreviate that LP. And that is given information. If it's given to us, then we can just go ahead and assume that it's true from the very beginning. All right. The other thing I like to do with proofs is I know where it needs to end. Something about this needs to be my last statement of my proof. So they are supplementary, meaning angle 1 and angle 2 are supplementary. So I know where the proof needs to start and I know where it needs to end. It's that middle section and how to get there that becomes a little bit tricky. And I don't really know the reason for this yet. So I'm going to leave the reason side of this blank because I don't know. Since I don't know what comes before this, I don't necessarily know how I'll get there or what my reason will be. Now, I have an idea of how I'm going to get there, right? How do we show that 2 things are supplementary? Well, we show that the measurements of the angles are equal, right? Or not equal. We show that the measurements add to 180. So I got an idea that the way I'm going to be able to say this is by saying the measurement of angle 1 plus the measurement of angle 2 is equal to 180 degrees. If I can show that, then I can say this. This is kind of what I meant earlier when I was saying these proofs aren't going to work the same as before. We're not going to just start at the top, work our way down, and then have a conclusion. We're going to kind of have to start at the top, know where we end, and kind of work our way from both sides until we have a chain of reasoning between them. At least that's one way to do it. Okay, keeping in mind, I need to get here. I need to show that those add to 180. Well, remembering my plan, I know that this angle, the straight line, I know that the measurement of angle COA is equal to 180 degrees because that is the definition of a straight angle. We know that a straight angle has to measure 180 degrees. And since we can see it in the picture that it is a straight angle, it's a straight line, then we can use that definition there. All right. The other thing we can do is we can actually set up an equation using the angle addition postulate. So I know that the measurement of angle COA would be equal to the measurement of angle 1 plus the measurement of angle 2. And that is using the angle addition postulate. Because I know that angle COA is the same as angle 1 plus angle 2. I'm going to draw some lines here just to separate this and keep it organized. All right. Now the question is, do I need another step between these, or are these sufficiently connected that I could sort of make this happen? And I view it as kind of having two options here in terms of what I could do. I could use either the substitution property. I could substitute 180 degrees in for the measurement of angle COA, and then I would end up with this equation. That's the way I'm going to do it. That's one way. Or I could also view this possibly using the transitive property. I know that the measurement of 1 plus the measurement of 2 equals COA, and COA equals 180, then I can kind of shortcut that using the transitive property. So I could say the measurement of 1 plus the measurement of 2 equals 180. I prefer substitution, and being able to say this is the substitution property, which is what I'm kind of showing with that arrow. I'm replacing 180 degrees for the measurement of angle COA because those things are equal. Substitution property of equality. And then, since the two angles add to 180, I know that they have to be supplementary because that is the definition of supplementary angles. Definition of supplementary angles. Our textbook uses this abbreviation for angles a lot, a little angle with an S on it. So I'm just going to use it here, angle, S, angles. Again, it's not a long proof. It only took me 5 steps. I mean, we probably solved equations that took just as many steps, but it was a lot more complicated than just solving an equation. And that's going to be the difficulty here, is that these aren't always going to be very, very straightforward. It's going to take us some time to be able to construct these on our own. I'm going to leave this up for a second. So I want to make sure that people are kind of understanding the basic ideas of how to approach a proof. I try to talk about some important concepts here, but I want to look at it again and kind of how you should kind of go through this process, especially if you're having trouble with it. So here's kind of a basic outline of a proof. You have your given information up top. Generally, to make things simpler, If I have multiple pieces of given information, so if our hypothesis has multiple parts to it, or another way that proofs will be structured is you'll just be given several statements that are true. Um, I just like to list all of the given information at the beginning. So however many steps that takes, it can be multiple steps if there's lots of given information, or it could just be one. It just depends. And then the second thing I like to do is, I don't know how long my proof is going to be, but I like to keep in mind, where am I going? What is the conclusion of this proof? And not only that, but my conclusion might be something like, these two angles are supplementary, like we had in the previous proof. I also want to know what might be right before that. What's sort of the mathematical equation that could come up that would show they were supplementary? So in that last one, instead of, I kind of added this as a step right before my conclusion that the two angles could add to 180, because that was kind of the mathematical way that I would show that they were supplementary. So know where you're going and know what you would need to show to get there. That's kind of what I'm saying with this. Once you've done that, the middle part is where kind of the real difficulty is going to come in. We need to figure out, how can we get from that limited starting information down to the conclusion? And we can't make any assumptions. We have to show it using definitions and properties that we know to be true. We can't just assume something based on like the picture, or like, yeah, that seems obvious, so we can just say it. We have to show it in this really rigorous way, which is tricky. And this is where making at least a little bit of plan about it is going to be important. Okay, so I'm going to clear this, and let's try another proof. This one's going to be a little bit of an easier proof. You might be able to, it's an easy but technical proof. All right, so we have, if angle 1 and angle 2 are right angles, this is our hypothesis, this is our given information. Keep doing that. So this is what we're starting off with. Angle 1 and angle 2 are right angles, and that is given to us, so given information. And what we're trying to prove is that those two angles are congruent. So we're trying to show that angle 1 is congruent to angle 2. That's where we're going to end up. Angle 1 is congruent to angle 2. I don't know how I'm going to get there yet. Now, the step before that is probably that their measurements are equal, that the measurement of angle 1 is equal to the measurement of angle 2. Because that's how we show congruence. We show that their measurements are equal. All right, so I've got kind of a, oops, I wanted that to be a line. I've got kind of an outline, at least, for what the beginning of my proof is going to look like and what the end of my proof is going to look like. I'm missing a few things, and I'm missing that middle section, which can be a little bit tricky. So this is not a difficult proof, but I did say that it is kind of technical. All right, so if angle 1 and angle 2 are right angles, that means we know that their measurements are 90 degrees, right? So that means we know the measurement of angle 1 is 90 degrees, and the measurement of angle 2 is 90 degrees. And that's because we knew they were right angles, right? So that's the definition of a right angle. Okay. Well, since we know that the measurement of angle 1 is equal to 90, and the measurement of angle 2 is equal to 90, keeping in mind where we're going, we want to get here. We want to say that measurement of angle 1 is equal to the measurement of angle 2. We actually sort of are almost done. It may not be obvious here, but we could sort of create a chain of equality. So this is kind of some work off to the side. But using just these two statements, I could create a chain that would show me that angle 1 and angle 2 are equal, right? Since the measurement of angle 1 is equal to 90, and 90 is equal to the measurement of angle 2, I can create sort of this chain where these three things are all equal to each other. Therefore, using the transitive property of equality, I'm allowed to just say that those two angles are equal. Transitive property of equality. So I'm allowed to make this statement because just based on what I've already stated in my proof, I can create this chain that shows those two things would have to be equal to each other. So I'm kind of demonstrating how I use the transitive property there. You don't need to include this in your proof. Most proofs would not include this. I'm just kind of showing my thinking there about how I use this statement to make this statement using the transitive property of equality. And then the final step, since the measurements were equal, that means that we were allowed to say that they are congruent to one another. This is a very technical step to go from here to here that, again, is perhaps not strictly necessary, and in the future we might gloss over some of steps like this. For right now, this is the definition of congruent angles. If the measurements are equal, then we can say they're congruent. That's what it means to be congruent. Okay. Again, a short proof, not too complicated. In fact, if I just asked you to sort of explain this, you probably would have said very similar things to this. You would have said, well, since they're both right angles, that means that they equal 90. And so since they both equal 90, then they would have to be congruent to each other. And that's pretty much what this proof is saying, just in a very specific, very rigorous way, and talking about the definitions of terms that we know and using properties of equality and things like that. That's what these proofs are going to be like, at least in the beginning, when we're kind of proving some of these basic ideas. Another name for this right here, this conditional statement, is called the right angle congruence theorem. Right angle congruence theorem. Basically, the right angle congruence theorem says that all right angles are congruent. If this is a right angle and this is a right angle, they're congruent to one another no matter what. Because they're both right angles, then they have to be congruent to one another. And the great thing about what we're doing here and what geometry does is once you prove something like this, then you can use it in other proofs. So once we have proved this particular statement, now we don't need to go through these steps to say that since 1 and 2 are right angles, they're congruent. We can just say, we know they're congruent, so we can just use this as our reasoning for it. We can use this as one of our reasons. And as we kind of build more and more of these basic concepts, we won't necessarily have to do these really technical things that are going on right here. We could go straight from step 1 here down to step 4. Since they're right angles, they are congruent. And that's kind of how we build more and more complicated ideas, by kind of starting with the simple and getting more detailed from there. All right, we're going to stop right there. Got about a minute left. I did update the Google Classroom page with the homework and such, so you should find everything there.